Hi, myself Samaresh Bera. I'm going to present our recent work on network slicing in 5G edge networks with controlled slice redistributions. This is the extended version of the talk in CNSM 2021. The network slicing is the creation of multiple logical networks on top of the physical network, and each logical network is dedicated to provide specific services. So for example, we have the physical network and this is virtualized. So that means all the networking resources of the physical network are virtualized. And on top of this physical network, we have different logical networks, that is the slices, to provide specific services. So in this example, we have three different slices, slice 1, slice 2, and slice 3. They are configured to provide differentiated services in the network. For example, slice 1 can be configured to provide broadband service. Slice 2 can be configured to provide services to the latency critical and reliable applications, and so on. So we have three different network instances in the network, one for slice 1, another for slice 2, and the other for slice 3. In this work, we focus on 5G edge network that consists of edge clouds, non-edge cloud nodes, and the links between the nodes. The edge cloud nodes are facilitated with compute and storage resources, and these compute and storage resources are utilized to host the virtual network functions associated with the slice request. The non-edge cloud nodes simply forward traffic in the network, and we have links between the nodes with certain bandwidth to forward the traffic associated with slice request. So if we consider the example here, we have nodes A, B, D, F. These are the non-edge cloud nodes. They simply forward traffic in the network, and the nodes C and E are facilitated with some compute and storage resources to host the virtual network functions. So these nodes are treated as edge clouds. Further, we have the links. For example, the link between node A and C has certain bandwidth to forward the traffic. We have slice request with bandwidth, compute, and storage requirements. Also, the slice request is associated with a reward if the request is served by the network operator. So our objective is to maximize the total reward by serving the incoming slice request based on the available network resources and the slice specific requirements in terms of bandwidth, compute, and storage requirements. So let us consider an example with initial slice request assignment. So let us say we have two slice requests. One is in red color, the other one is green color. So the red color slice is assigned to edge cloud 2 for the compute and storage resources, and the green color is one. The green color one is assigned to edge cloud 1. However, on receiving new slice request, the existing slice can be redistributed in the network. So in this example, we see that the green color slice is redistributed from edge cloud 1 to edge cloud 2, and we are able to admit a new request to the edge cloud 1. So we see that the slice redistribution helps to in maximizing the total reward by accommodating more number of slice requests. However, the active slice redistribution entails significant operational cost in terms of migration time, interstate dependency, and additional bandwidth. So in terms of migration time, that is the virtual network functions associated with a slice needs to be migrated from one location to another, and this migration involves some processing time. So this is treated as migration time. Also, we have the dependencies between the virtual network functions associated with the slice. So we need to consider the stateful operation of the VNF migration from one location to another. And finally, we also need additional bandwidth to migrate the VNFs from one location to another. So in this work, our contributions are as follows. We allow active slice redistribution while controlling the number of active slice redistribution in the network. And to control this active slice redistribution, we introduce a penalty function. And we note that this active slice redistribution is not considered in the literature. Further, we design two comprehensive cost functions that captures the bandwidth, storage, and compute resources in the network to answer two questions: whether to admit a slice request in the network and which edge cloud to serve the admitted slice request. Then we propose a multi-hop traffic routing algorithm to determine how to route the traffic in the network, and this is not considered in the literature. The existing works consider the single hop traffic routing in the 5G edge network. So we formulated the optimization problem as the maximization of the total reward minus the penalty term associated with the active slice redistribution. So if we look at the reward term, here we have zeta r, that is the reward associated with the slice request r, and we have the binary variable xkr, that is the whether request r is assigned to the edge cloud k, minus the penalty term where we have sigma as the penalty factor, and we have two variables. One is the current assignment and the other tilde xkr is the previous assignment. So if the assignment changes, we have the redistribution penalty. We have the following constants such as storage and compute constant at the edge clouds. We have bandwidth constant at the links in the network. Further, we note that a slice request is assigned to at most one edge cloud in the network. And finally, we have the flow conservation rule. So this optimization problem is NP-hard. Therefore, we propose a polynomial-time greedy heuristic approach that consists of 4 phases: active slice identification, request selection, edge cloud selection, and forwarding path selection. So in the phase 1, that is active slice identification, we identify a subset of active slices that can be redistributed or dropped based on a cost function. So this cost function, we design a comprehensive cost function that is presented later. Further, in the phase 2, the request selection phase identifies the sequence of active and new requests to be served in the network. So for the identified request, in phase 3, we determine the edge cloud to be selected to serve the request. So to select the edge cloud, we design another cost function considering the slice specific requirements. And in the final phase, for a selected edge cloud and the request, we select the forwarding path for traffic routing associated with the slice. So let us go through each of these phases in detail. So for slice request selection, we design a comprehensive weighted cost function that consists of bandwidth, storage, and compute cost. So in terms of bandwidth, we have BR, that is the bandwidth requirement by the request R, and Bmax is the maximum bandwidth requirement from the set of new requests. Similarly, for the storage and compute, we have predefined constants alpha, beta, and gamma. These are used to capture the relative importance between the bandwidth, storage, and compute cost. So based on this cost function, we identify the active slices for potential redistribution. So we sort the active slice request based on the cost function and the reward associated with the request, and we earmark a subset of requests for potential redistribution. Then we include these active slices that are considered for potential redistribution with the set of new requests, and we sort the new and identified new active request. Finally, we check each request for admission from the sorted list based on the reward and the cost function. So if we look at the example here, let us say we have slice requests, active slices 3, 5, 1, 4, 2, and we consider that 40% active slices can be redistributed. So here request 4 and 2 are identified active slices for potential redistribution, and we include these new active slices with the new, set of new requests. So we have 4, 2, 6, 7 as the set of new requests, and then based on the cost function and the reward associated with the request, we sort the request, and each request from the sorted list is sequentially checked. So request 4 is checked first, then 6, then 2, and so on. So once we identified the request for admission, we need to select the edge cloud to serve the slice request. So to select the edge cloud, we again design another comprehensive cost function that consists of bandwidth, storage, and compute cost at the edge clouds. Alpha, beta, and gamma are the predefined constants used to capture the relative importance between the bandwidth, storage, and compute. And we see that the bandwidth of incoming links to the EC is considered to have more aggregated paths to reach the edge cloud. So if we look at the example here, let us say we have different edge clouds such as 1, 2, 3, 4, 5, and the cost based on this cost function. So the edge cloud with the minimum cost is selected to serve the request. So in the last page, we focus on forwarding path selection for a given request and the selected EC with minimum cost. So to select the forwarding path, we obtain a residual network based on the bandwidth requirement and the available bandwidth in the network. And then on this residual network, we calculate the forwarding path based on the Dijkstra's shortest path algorithm, and where the link weight is considered as the ratio between the initial bandwidth and the residual bandwidth of the link. So if we look at the example here, let us say we have request bandwidth requirement is 5 and the network with residual bandwidth. So the links that do not meet the bandwidth required by the request are pruned, and then in the residual network we apply the Dijkstra's shortest path algorithm to determine the forwarding path from the source to the selected edge cloud. To evaluate the performance of the proposed scheme, we consider a quadratic penalty function. So here xkr is the current assignment and tilde xkr is the previous assignment. So if they are different, then it incurs the penalty. So from the quadratic penalty function, we see that the more number of slice redistribution, the larger is the penalty. However, we can choose any penalty function to consider the effect of active slice redistribution in the network. The values of the parameters are considered from the literature, and the predefined constants for the cost function associated with the request selection and the edge cloud selection are chosen manually. Further, we to evaluate the performance, we use ATTMPLS network topology from the Internet Topology Zoo, and we select the certain percentage of edge clouds in the network. So here we plot the total reward compared to the optimal solution and the proposed scheme called reset. So in the x-axis we have arrival rate, that is the number of requests per second arrived to the network. In the y-axis we have total reward obtained by the network operators on admitting the slice request. We have three different schemes: optimal solution by solving the optimization problem. So we solve the optimization problem using IBM CPLEX optimizer. And we have two variants of the proposed scheme. One is with 5% active slice redistribution and the other one with 10% active slice redistribution. Further, we have considered two penalty factors. One is with 0 penalty and the other one with 0.5 penalty. And eta here is the percentage of edge clouds selected in the network. So for the given ATT-MPLS network, we selected 10% edge clouds in the network that have more number of adjacent links. So we see that the proposed scheme reset is competitive with the optimal solution, and the total reward is within the 15 to 25% of the optimal solution. So further, we see as the number of requests per second is increased, the total reward is decreased in both the cases. This is because that we consider total 500 requests in the network, and when we have large arrival rate, very less number of requests are served by the network and rest of the requests are dropped. So that's why we have less reward. Further, we evaluated the percentage of active slice redistribution in the network using the optimal solution and the proposed scheme reset. So similar to the previous one, we have in the x-axis we have arrival rate, that is the number of requests per second, the percentage of active slice redistribution in the y-axis, and we have three different schemes. One is the optimal solution, then the two variants of the proposed solution, one with 5% active slice redistribution, the other one with 10% active slice redistribution. We also have two penalties with that is without any penalty and 0.5 penalty factor, and 10% edge clouds in the network. So we see that from the figures, the proposed scheme reset entails far fewer slice redistribution than the optimal solution. And further, we see that using the optimal solution, the slice redistribution decreased with increased penalty. So if we look here, without penalty, we have more than 100% active slice redistribution. However, when the penalty increased, percentage of slice redistribution is decreased. Then we evaluate, we measure the computation time using the optimal solution and the proposed scheme reset. So here in the x-axis we have the arrival rate, that is the request per second. In the y-axis we have computation time in seconds. So we plot it in log scale. We have three schemes. One is the optimal solution and two variants of the proposed scheme. One with 5% active slice redistribution, the other one with 10% active slice redistribution. And we see that the computation time by the proposed scheme is smaller by 2 orders of magnitude than that of the optimal solution. So once we see that the proposed scheme is competitive with the optimal solution, then we focus on the performance of the proposed scheme with large scale deployment, and we compare the proposed scheme with two benchmark schemes. One is the reward and other one is the FCFS. So in case of reward, the requests are preferred based on their reward. So the request with highest reward is checked first for admission, then the second one, then third one, and so on. And in case of FCFS, as the name suggests, so first come first serve, first serve. So the requests are served based on their arrival to the network. And for all these schemes, the proposed scheme reset and reward and FCFS, we consider the redistribution percentage of active slices as 5%. So that means 5% active slices are considered for potential redistribution. So we plot the reward using the schemes reset, reward, and FCFS. So in the x-axis we have arrival rate, that is the number of requests per second, and in the y-axis we have total reward. So we have three different schemes. One is the proposed scheme reset, then the reward with green color, and the FCFS scheme in blue color. So we have two variants. One is two penalty factors are considered, one with 0 penalty and other one with 0.5 penalty. So 0 penalty, and here we have 0.5, 0.5. Further, we increase the percentage of EC from 10% to 20%. So we have four plots, one with 0 penalty, 10% edge cloud, 0 penalty, 20% edge cloud, 0.5 penalty with 10% edge cloud, and 0.5 penalty, 20% edge cloud. And in all cases, we see that with more number of edge clouds in the network, the reward increases. So if we see here, we have 10% edge clouds in the network. However, when it is increased to 20%, the total reward is increased. Further, we also see that the proposed scheme reset achieves higher reward than the benchmark schemes reward and FCFS in all schemes, all cases. So this is the reason. This is because the proposed scheme reset considers the comprehensive cost function that accounts the bandwidth, storage, and compute resources in the network, and also the bandwidth, compute, and storage requirements by the requests. So it doesn't consider the reward only, but also it considers the requirements. So that's why the total reward is using the proposed scheme reset is higher than the benchmark schemes. Further, we also compare the percentage of slice redistribution using the using three different schemes. One is with the proposed scheme, the two benchmark scheme. One is the reward and FCFS. In the x-axis, we have arrival rate, that is the number of requests per second, and in the y-axis, we have percentage of slice redistribution in the network. So similar to the previous one, we have 0 penalty, 10% edge cloud, 0.5 penalty, 10% edge cloud, 0 penalty with 20% edge cloud, 0.5 penalty, and 20% edge cloud. So if we see here, we see that the proposed scheme FCFS entails fewer slice redistribution than the proposed scheme reset and the reward. So the reason is in the scheme, FCFS scheme, the requests are always served based on their arrival. So even if we redistribute some of the active slice redistribution, or even if we consider some of the active slices for potential redistribution, they are preferred first for admission. So that's why the percentage of redistribution is less compared to the reward and the proposed scheme reset. However, we see that when the percentage of edge cloud is increased from 10% to 20%, the percentage of slice redistribution is also increased. So in this work, we propose 5G edge network slicing with controlled active slice redistribution that accounts multidimensional resources such as bandwidth, compute, and storage resources in the network. The proposed scheme reset achieves competitive reward compared to the optimal solution while incurring far fewer slice redistributions. The computation time of the proposed scheme is smaller by 2 orders of magnitude than the optimal solution. Further, the proposed scheme achieves more reward compared to the two benchmark schemes considered in this work. As a future scope of this work, we plan to use Bayesian optimization for automatically determining the values of the constants of for the request selection and the edge cloud selection. And we also plan to focus on end-to-end network slicing, considering 5G radio access network, edge, and core networks. So this problem is much more challenging while we consider end-to-end network slicing because of the dynamic nature of the radio access network. So thank you, and please do read our paper. If you have any questions, please feel free to email me to my email ID. Thank you.